Hi everybody, I am Scott Bednar.
And I'm Jessie Wild with NASA 360.
And we are very excited today to bring you a special event. It's the Mars Ice Challenge, and it's happening behind us here from NASA's Langley Research Center.
And while it might not look like the surface of Mars behind us, students have traveled in from around the country and they're attempting to solve a Mars exploration dilemma.
So let's go get a closer look?
Let's do it.
Let's do it. So several university teams have actually come to NASA from all across the country to compete in the Mars Ice Challenge. What's their goal? Well, they want to create a prototype system that's capable of digging through simulated Martian soil. They need to access a subsurface ice, and then they need to melt that ice into water.
As we look forward to the future of deep space exploration, accessing resources like water is going to be crucial for humans to survive on other planets. Teams have been tasked today with designing an ice and water harvesting system for use on Mars. And today they're testing their systems out for the first time in a head-to-head competition.
All right, let's get a closer look at one of these Mars ice drilling systems and get a better feel for how the Mars Ice Challenge works. So the Mars Ice Challenge actually has two main components. You've got design and you've got demonstration. First, every team that's here today had to design a system that was capable of extracting and harvesting ice and water on the red planet. Okay, then you've got demonstration. That's basically what you're looking at here is a technology demonstration. This team's got a drill, and that drill needs to dig down into a fake Martian dirt. And once it does that, it needs to reach ice. Once it reaches that ice, it needs to somehow figure out a way to extract it, harvest it, bring it up, turn it into water. And that's basically how you win the Mars Ice Challenge. In fact, let me give you a different view over here. I want to give you a cross-section view of one of these big blue bins, okay? So these big blue bins, every team has one of these. And from about here to here, we have simulated Martian regolith. That's basically just fake dirt, fake Martian dirt. At about this point, we've got a big block of ice. So each team needs to somehow get through all of that Martian regolith to that ice. Once they get there, they need to extract it, they need to harvest it, and they need to turn it into water. Once they do that, if everything goes to plan, that water should come out this tube right here, and the judges will then assign points to how much water is in their bucket, and based on different inputs, that's how you win the Mars Ice Challenge. It's actually very exciting. So let's move on to Jessie, who wants to go chat with somebody who knows a little bit more about the mysterious red planet.
Thank you, Scott. It is very exciting. We're going to talk to Jerry Sanders. He is a NASA expert on in situ resource utilization. So Jerry's going to explain a little bit about what that is. But the basic idea is that as we move further out into our solar system, it's really important that we're able to harvest resources from other planets for our human use. So Jerry, thank you so much for being with us.
Oh, no problem.
So let's start off by what is the Mars Ice Challenge all about, and why do we care about water on Mars?
Well, the Mars Ice Challenge is all about having teams try to solve a problem that we ourselves in NASA are starting to consider. And that is Mars has potentially subsurface ice that is mineable. But it is a challenge. It's below the surface. You have to go through overburden. It's a very cold environment. And so these teams are giving us an idea on different ways in which NASA might pursue that particular goal. Now, why do we want water is another question, very good one. Water is a fabulous resource with lots of different applications. Obviously, drinking water is one of them. It's a fantastic radiation shield. So here, instead of bringing big metal blocks and heavy habitats, we could have a habitat with a hollow wall that we fill up with water from the local materials. Provides great radiation shielding. The really big advantage is turning it into rocket fuel and propellants to help the astronauts get off of the Mars surface.
Can you tell me a little bit more about in situ resource utilization?
Well, it's a very fancy term that we use for basically how do we live off the land? How do we get into a mode of not having to take everything from Earth for our exploration? And a good analogy is camping versus going and settling. So if you're going camping, you're going to bring your tent and you're going to bring a canteen and water bottles. You're going to bring freeze-dried food, and you know you may use local materials like firewood, but you know something along those lines. However, if you're going to go there for a long period of time, you're going to bring things like seeds and shovels and hatchets so that you can build your habitat and maybe drill for a well and things like that. So it's a different mindset. But it allows you to actually stay there for a longer period of time. With a camping trip, you've only carried enough stuff for a few days maybe.
And it seems like there would be a lot of challenges associated with this. What are some of the challenges that we see on Mars that the students were asked to face today?
Well, first of all, they were asked to make designs that were representative of operating on Mars, which has a much lower pressure atmosphere, about 1/100th of what we have here on Earth, much colder temperatures as well that they have to experience. So even though they built hardware that's obviously operating in a hangar here at Langley, their original forethought had to be, what would the system be like on Mars? The other challenge is there is an overburden or material on top of the ice. How do we get through that? It could be very cold material, there's rocks in it. Our missions are typically power limited, and mass limited, because we can't send heavy bulldozers. So the teams were challenged in terms of both how much mass their hardware could be, as well as how much power they could use.
And how will NASA use these student ideas?
Well, it's a great learning experience in terms of being able to see a lot of different options. When NASA starts a study, a lot of times they'll pick maybe 2-3 different ideas and spend a lot of time designing and working on it. What this does is we have 10 teams out here trying different ideas, different iterations, so we can now kind of pick and choose. Hey, which ones worked well, which ones didn't? We can focus our efforts along those lines, maybe enrich some of the designs, maybe work with some of the teams downstream.
And I know you've had a chance to walk around and see some of the designs. What are your thoughts on them?
I'm impressed. I've worked in the field for 20 years. I'm an aerospace engineer by trade, so I've had to learn over time a lot of different things. These teams were basically set up in 1 or 2 semesters, had to learn something completely new that's probably outside their curriculum, and under those circumstances, I'm impressed with the number of ideas and in fact that we have 4 teams on the board that have water, and it looks like 2 just recently are in the process of extracting water. It says that there's a lot of ideas that are actually viable.
Well, great. Thank you so much, Jerry. We're going to go take a look at some of these systems in action. Thank you for being with us.
No problem.
I'm going to hand it back over to Scott, and he's going to talk to one of the teams and actually see their drilling system.
I am. I'm very excited. By the way, if you are just joining us, we are live from NASA's Mars Ice Challenge, where university teams are drilling through simulated Martian soil in an attempt to extract ice below. Now, if you come with me over here, I want to introduce you to Nikki from Alfred University in upstate New York. Hi, Nikki. How are you? Come on down.
I'm good. How are you?
Good. So I understand yesterday you had an issue with your motors on your system. Can you tell me a little bit what happened?
Yeah, pretty much everything went wrong. The servos went wrong, the encoders, coding was wrong. So we had to go through that a little bit, try to figure everything out. So we spent most of yesterday doing that. We ended up scrapping the whole motors idea. We jerry-rigged some drill systems with different triggers. So yeah, that's pretty much what we ended up doing.
So you're up and running again?
Yeah, for now.
Okay, so can you actually walk me through your drilling system? How does it work? How do you intend to get ice below this fake Martian regolith?
All right, so basically our system works like a corn auger. So as you can see with the system right now, the pitch between the flukes of the auger itself are too steep. When we drill at a vertical level, the material will just want to go right back down. So we put it at an angle so that way it helps assist the gravity pulling it up. So that's kind of our drilling method for that. Our hopper door, which is that clear thing wrapped with a white wire, that stays closed while the while the ice is going through. It's open when the dirt's going through.
Okay. So how are you actually getting the ice to go through that? Is it coming up the auger?
Yep.
Gotcha. So how does your system differ from other team systems? They all look so different here.
So the biggest difference between our system is that it's only one drill, and that is at an angle. No other teams are drilling at an angle. No one has in the past. So that's kind of what's unique for our system.
And what benefit do you think that gives you?
It helps us a lot with the gravity of pulling everything up. Otherwise, it just wants to slide back down. This will keep the system enclosed off, which is great for when you're actually taking it onto Mars. The entire system needs to be sealed off, so it's all practical. It's a really great path to flight for it.
Awesome. Well, hey, best of luck to you and your entire team. Thank you so much.
Thank you, too.
All right, go get that water. So why don't we take a little bit of a tour of the pit right now and see a few other teams' Mars drilling machines.
That is a great idea.
By the way, again, if you are just joining us, we are live from NASA's Mars Ice Challenge, where university teams are drilling through simulated Martian dirt in an attempt to extract the ice below it. One-day systems like these could be used to extract water below the surface of Mars, the Moon, or even other planetary bodies.
So let's take a little walk throughout. As we walk around today, and I want you to notice that all of the different drilling systems are unique. What's really interesting is that students have the same task and they all came up with really different ideas. So it's very cool to see. And it's actually one of the reasons that we try to have student competitions like this is because they do bring these new, fresh ideas. And I think they're also enjoying seeing each other's ideas and
Absolutely.
Collaborating. And today is day 2 of the competition. So yesterday was day 1, which was a hands-on. So that basically meant that they could kind of make adjustments to the drilling system, and water that they collected yesterday was therefore worth a little bit less points. Today is day 2, the final day of the competition and the most challenging day. And it basically means that they're hands off. They are remote controlling their drills. So water harvested today is actually worth 3 times the points.
So we want to strike water today.
We do, and I think a team is actually about to strike water.
So most of these university teams are actually using an auger system like the one we just saw with Team Alfred University. It's basically just a drill, and they're using it to dig through the simulated Martian dirt to get to that ice below. But that's pretty much where the similarities end. Some teams are harvesting ice and melting it in separate chambers. Some might melt the ice directly beneath the soil, and others let the ice condense into a gas and then convert it back to water somewhere else in their system.
We're going to talk to another team. We're going to talk to Aaron from the University of Tennessee at Knoxville. And it looks like they're actually getting very close to getting water. Aaron, thank you so much for being with us.
Hey, thank you.
So tell me, what school are you from?
I'm from University of Tennessee of Knoxville.
And tell me about your drilling system.
Okay, so right here we have a 2-tool head system. We have an auger is what we call it. As you see, it has a spiral like most people have. We have a drill. We have made some modifications based upon how our drilling went yesterday. We ran into some issues with whenever we had a PVC tube around it, we actually were pressing the mud rather than actually being able to excavate it out. So we made that modification, cut that PVC off, and we're using it simply as a digger. It's actually dispersing the dirt out of our hole. And as you can see right here, our ice melter is actually melting the ice, and we're getting some water actually. Even though it's dirty, we still got water.
Congratulations. When did you get water?
About 5 minutes ago.
Very exciting.
We have a leak, but I mean, we're just really happy we got water and we succeeded in our minds.
So what was it like being faced with challenges like that under pressure?
We were really concerned about the whole operation of it working, just the entire system, because we did testing, but we didn't do as extreme testing as we have had here. So we were deeply concerned with that, but we have been able to prove that it works. We've been able to succeed under the pressure. So we're very pleased with how our performance has gone.
And how does your drilling system differ from some of the other systems that you've seen here?
Yeah, so our drilling system is different because we have a lot larger sized augers, what we call it. At first, initially, we were trying to travel it up the auger, and so that we disperse out of a chute at the very top so that we can get it outside of our entire volume that we're using, so we don't have to have interference with our water system. As you can see, based on the modifications we've made, it's slightly similar to how everybody else's are, but at least our melting device is much different, since most people are using what I believe is a rock weld system, and they are dropping a cylinder down into the smaller diameter hole and being able to kind of melt the surrounding area and pump it out.
How does yours work in comparison with that?
So ours actually has some extreme temperature copper pin fins on the bottom of it that allow a smooth surface whenever we touch down onto the ice. And that also enables it to withstand higher temperatures. Copper is very good conductor, so whenever we do apply temperature to that, it can heat up to insane temperatures to allow us to heat it up and ramp really quickly to melt the ice.
Perfect. Well, thank you so much for talking with us, and congratulations on getting water. Just moments
congratulations.
before.
I just wanted to come over and see it. So are we getting a lot of water, or?
Well, as you can see in the bucket, we actually have had a leak. So at first we were having a lot of water. We have slowed down, but
Hey, it's
you know,
still
we're
water
happy,
nonetheless.
You know?
Congratulations.
Thank you.
Congratulations. I'm going to hand it back over to Scott. He's going to talk to someone who can tell us a little bit more about the Mars Ice Challenge and how you can get involved.
So Miss Shelley Spears knows a lot about the Mars Ice Challenge, and that's basically because she put this whole event together. Hey, Shelley, can I grab you over here for a moment? How you doing?
Hi, how you doing, Scott?
Very good. So tell me, how are things going at the 2018 Mars Ice Challenge?
Amazing. We're having so much fun. The teams are really operational. We have 6 teams operating right now, which is better than we did last year. These things take time to develop over a period of time. So, and we have 4 teams that have already harvested water today. Today's the hardest day.
So what are we expecting by the end of the day?
We're expecting to see, I would say, 70 to 80% of the teams here that are have operational systems, meaning they're operating remotely. Some of the systems have already gone down, so they're going to actually go back in and start operating with a hands-on approach. We had one team that had an engine, a motor that burned up, but that's okay. They're getting their system back online, and then we're going to see what it can do. So, but we're excited about the number of teams that are actually operational, remote controlled. We see a lot of water. We're thrilled.
It's actually thrilling here on site. It's very enlivening. So why are competitions like the Mars Ice Challenge important?
The Mars Ice Challenge is important to NASA and to industry because these are technology capabilities that we are still developing. We're trying to figure out how to crack the code of ISRU, which is In Situ Resource Utilization, how to operate independent of Earth on the surface of Mars, on the surface of the Moon, and we need to understand what resources are available on those surfaces so that we can use them to sustain human life and to help with human space exploration on those environments.
Fantastic. So this whole Mars Ice Challenge falls under a program called RASCAL. Can you just tell me a little bit about what RASCAL is?
Happy to do it. So RASCAL stands for Revolutionary Aerospace Systems Concepts Academic Linkage. And basically what we do is that we have universities, teams across the country that are working on human scale system architecture competitions, analogs, technology demonstrations, and prototypes. It really depends on what NASA is interested in and how we craft that years, or there may be more than one competition a year depending on what we're looking at. This is a special edition focusing on ISRU. We'll have another one in 2 weeks down in Cocoa Beach, which is really focused on human scale system architectures related to the Deep Space Gateway, Deep Space Transport, and a lunar sample return. So those will be fun, 2 weeks.
And if you stay tuned to NASA 360's Facebook or Twitter pages, we'll be bringing you live coverage from that RASCAL competition down in Cocoa Beach, right?
We're excited about that. So we expect to see a lot of universities, students, anybody that's interested at all in human space exploration and these mission architectures have a big audience for it. And I imagine there's going to be some excited parents too who are going to be able to see their students presenting. So we're happy to bring that live to the public and to families all over.
So there are a lot of students actually across the country watching this today live. If they want to get involved in something like the Mars Ice Challenge or in a RASCAL Challenge, how would they go about doing that?
Well, sure, especially that they're involved in universities because this is designed as a university competition. So I would encourage them to look in their department, engineering department, aerospace engineering, mechanical engineering, electrical engineering. We get the word out to all the department chairs at all the research and engineering schools across the country. And they can also find competitions at rascal.nianet.org. We launch all the themes in the summer. That includes the requirements, the constraints that NASA and the experts have put together on what the themes will be like and what we're asking our university partners to do. These are typically senior capstone design projects. So these are seniors who have been getting ready to graduate in a year. So next May or June they'll be graduating, and they'll work on this throughout the year as their senior capstone design project. We also have graduate students that work on this. Our team from MIT are all grad students, for example. So whether you're undergrad or grad, we welcome you to join the challenge.
Fantastic. There are plenty of ways to get involved, folks. So, Shelley, thank you so much. I wish you luck with the best of the challenge. Thanks for joining us today.
Thanks, Scott.
So, by the way, if anybody is just joining us, we are live from the NASA Mars Ice Challenge, where university teams are actually drilling through simulated Martian dirt in an attempt to extract the ice below it.
We've actually seen a team collect water
We
just
have.
in the last 10 minutes. Very cool. Now, part of exploring the solar system is living off the land wherever we go. This is known as in situ resource utilization, and it's going to become increasingly important the farther that we travel away from our home planet. Future astronauts need to be able to collect resources while they're in space and turn them into things that we can use: breathable air, rocket propellants, building materials, and of course, water.
So the Mars Ice Challenge consists of two main components. Okay, you've got design and you've got demonstration. First, teams need to design an ice and water harvesting system that's capable of being used on the surface of Mars. Then they have to develop a technology demonstration of that Martian system, but modify it for use on Earth, and that's really not easy. You see, the atmosphere and gravitational pull on Mars and Earth are very different from each other, so building a system for Mars that we then test on Earth is no easy task. That's actually part of what makes the Mars Ice Challenge, well, so challenging.
Should we talk to another team
Let's
and
do it.
take a look at their drilling system?
Let's do it.
All right, let's go talk to Sean from West Virginia University. Sean, thank you so much for being with us.
Yeah, no problem.
So what school are you from?
I'm from West Virginia University.
And tell me a little bit about your drilling system.
Our drilling system, sorry, let me move out of here. It goes down, it chips up the ice underneath the regolith, and then gathers up those chips inside the casing for the auger. Then it transfers them over to our melting bucket, which then passes through a 1 micron filter to clean out all the dirt.
And have you had any challenges or difficulties as you've gone along?
We have had a lot of challenges. We try to make it pretty much autonomous, very little user input, but it was trying to keep itself too safe, so it wasn't going as far down as it should. We had a lot of learning difficulties. We're all mechanical engineers, and this is very much an electrical project, so we had to learn a lot about wiring and coding.
And how does your design differ from some of the other teams here?
A lot of the other teams are using either a two-probe design or are melting down inside the hole instead of gathering up the ice. We are trying to avoid that to prevent a whole bunch of mud from getting into our system and clogging it up.
Have you been able to get water yet?
We haven't gotten any water yet. Hopefully today we will, but yesterday with the autonomy issues we were having, it just made a whole bunch of mud as it was trying to protect itself from going too hard.
And so does the water have to be clean that you collect?
Has to be clean-ish. I believe for every 10 grams of debris inside the collection bucket, they will knock off a couple points. But we should get almost all of it with our filter.
And so being faced with these challenges under pressure, what has that been like? Has it been a big learning experience?
It has been a huge learning experience. Time management has been critical between my classes, my thesis, and this robot. So I've definitely learned how to manage my time a little bit better.
Great. Well, best of luck. I hope that you're able to get water today.
Thank you.
Thank you again for talking with us.
No problem.
I'm going to hand it back over to Scott, who is going to speak with a NASA expert on Mars.
I want to introduce everybody to someone who knows a lot about Mars. In fact, he might be the perfect person to talk to about the red planet, Mr. Rick Davis. Rick, it's good to see you again.
Scott, it's great to see you and your whole team. It's wonderful, actually.
Well, thank you. So I want to throw a big one at you. Why Mars? What is the big deal?
So Mars in terms of the ice drilling, or Mars as a destination?
As a destination, a place to go.
So Mars is about as hard as a challenge as the human species can pick up right now and actually do it, is my opinion. We've been to the moon, and the moon's an integral part of actually getting to Mars. But to give you a sense of scale, the moon's about 238,000 miles from Earth. The Mars is 100 million miles. You take that number, and that distance is just one factor that gives you a sense of how audacious that goal is. And so, it will push us on every level that we can possibly think of, not just technology, but in terms of how the culture operates, how we work together, how we do all of those things. In fact, I would even say, I'd like to talk a little bit about these teams right here. NASA by itself cannot do Mars. I would even say space agencies by themselves can't do it. It's going to take the creative ideas and sort of different perspectives that you really need across this planet. And these students bring different perspectives that we really need. And I think they are a generation that is used to interacting with people all over the globe. They're used to bringing in ideas from all over the place. They're used to 3D printing, so many things that many of us are not. And those may be ideas or cores of idea that we absolutely have to crack the nut of doing something as audacious as Mars.
So I'm sure you've already looked around at a lot of these student designs. Can you tell me about some of the unique systems that they've come up with?
So So the really cool part of this is that unlike a lot of challenges, we have actually structured this to build on the lessons learned from last year. Last year was the first time. But we have consciously asked the teams to share what they're learning with the other teams so that these new teams, or some are coming back, can actually build on that and take it to the next step. You know, I always say standing on the shoulders of giants. And the ones from last year are the giants, but we've also made subject matter experts available. And you see a lot of similar ideas, but they're all doing it differently, and they're fleshing out different concepts that we really need. In fact, we've even been talking in the last 2 days that there may even be specialized projects that we want universities to go look at so we can hone this down even faster.
So why do you think, and you kind of just spoke to this, but why do you think it's so important to engage students in challenges like this?
So I love that question. I would say there's a couple parts to it. One, they're bringing different perspectives. There's actually a more subtle reason about why it's important to engage students, because these are the people who are going to Mars. You know, if you're talking the 2030s, which I personally believe the human species is capable of, it is this generation that's doing it. You know, when you're an astronaut and you're going to Mars, you're in school now. And so and more to the point, this generation actually accepts Mars as happening. And so a lot of times I will use the phrase Mars is hard as a euphemism for Mars is impossible. It's not. The problem is you have to get past the point where you think it's impossible so you can actually start doing exactly what every single one of these teams is doing, figuring out how you do it. And once you believe it's possible, then magic starts to happen in terms of pulling all this stuff together. And that is exactly what I believe we're seeing here.
So Mars is closer than you think.
Mars is much closer than we think. And I'm not trying to downplay how hard it is. But I would say when you look at the aggregate amazing capabilities of the human race right now, it is not as big of a jump as it was in the early 1960s when they jumped to the moon for the first time. You know, we have massive capabilities now that really enable this audacious goal to be possible.
Such an exciting prospect. Well, Rick, I really, really appreciate talking with you today. Thank you so much.
Thank you guys. I mean, so I love what you all do, and I would just add this. This is a two-way conversation. We not only are trying to convey what we're doing here, but we need ideas from other people to help us figure out the path. And that's the only way it's going to happen. And so thank you.
Fantastic. Good luck with the rest of the competition.
NASA's discoveries in aeronautics and space exploration, science, and technology, they're transforming our understanding of ourselves, our planet, our solar system, and our universe.
Competitions like the Mars Ice Challenge really help push technological boundaries forward. And they inspire the next generation, some of whom you've actually seen here on the floor today.
That's absolutely right. There's an aircraft going overhead, so it's a little bit noisy in here.
We've got some jets here in this working hangar.
Now, we're surrounded by the researchers of tomorrow in here, and now just imagine what they can accomplish as we make the next giant leap for humankind.
We've seen a lot of exciting prototypes here today. Hold on, one more jet.
Another aircraft overhead.
A real working hangar here at NASA. These prototypes have been incredibly exciting. They've been complex, they've been out of the box, and it really could push forward some of NASA's goals as they look to the moon, Mars, and even beyond.
On behalf of NASA 360, I'm Jessie Wild.
And I'm Scott Bednar. Thank you so much for joining us today.
If you'd like to learn more about what NASA is up to, join us at nasa.gov/NASA360 or on Facebook and Twitter.
And remember, this is your space agency.
Get to know it.